Okay, in this video, I will show you how to find the maximum range, the maximum height, and the time of flight given the initial velocity of the object and the angle. So we are going to restrict ourselves to the canon to be at 0, 0. So the initial velocity, the initial position is 0 in the x and 0 in the y. That simplifies the problem tremendously. And we are going to calculate the maximum range, this number over here, 21.7, given the initial velocity and the angle. We are going to find analytical equation for r, which is going to be this distance, h, that is going to be this distance, and time of flight, that I will call it tau, that is going to be this time. If you put this over here, you can see that the time of flight is 1.75 seconds. The range is 21.55. And if we go over here to the top, the height is 3.77. So those are the equations as a function of the initial velocity and the angle that we are going to derive in this video. So this is the object is at 0, 0. At time 0 is moving with initial velocity v0 and angle theta. And we want to find this r, and we want to find this one looks like this r over 2 and h. So we want to find r, h, and tau, that is going to be the time of flight. Given v0, theta, and the acceleration of gravity. Okay, so let's put over here the equation for y is y0 plus v0 y t plus 1/2 acceleration in the y-axis times t, and the same kinematic equation for x times t. But the acceleration is only in the y-axis. It's only in the y-axis. And the magnitude of the acceleration is 9.9 meters per second. If you are at the surface of this planet, that's what we are going to call g. Positive 9.8 is the magnitude, that's g. So if we put the axis up like this, that's why this is negative over here. Because the initial position is 0, we cross this out. So we have v0 y t minus 1/2 gt squared. Here the initial is 0. There is no acceleration across. And the equation is this on the x-axis. Now we use trigonometry to find the components of the vector. This is the hypotenuse, v0, and this is the angle. So the x component is v0 cosine of the angle, and the y component is v0 sine of the angle. Remember, the sides are a fraction of the hypotenuse, and that fraction is sine or cosine depending if the angle is adjacent to the hypotenuse, to the angle, or is opposite to the angle. So finally, these are the equations. that we are going to use to derive anything in this in here. All right, for example, the time of flight is what is r at tau. So equation 2 becomes r, because I call it r, times tau. And now how to find tau? Tau is when y is 0. So equation 1, and you get b naught sine of the angle times t times tau, because it's tau. Just call it tau. The time of flight is no torque. As you can see, 1t cancel. You don't have to use the quadratic equation. And when y is 0, at what time that happens is 2b naught sine of the angle over g. All right, that's the first one. So we got, that's the time of flight. Another way of doing it is by symmetry, or again, you have to prove that it's symmetric over here. Kind of this circle. You could find when, at what time the ball is at the maximum. And if you put the velocity equation in the y, you know the velocity in the y-axis is 0 for an instant over here. And this is b naught sine of the angle minus gt. So that time is b naught sine of the angle over g. And twice that is tau. And you get exactly the same equation. You could also check that b naught is meters per second over meters per second squared, give you seconds. All right, so if we now substitute tau into this equation for r, b naught squared over g, and then you have 2 cosine of the angle, sine of the angle, and this is sine of twice the angle. And how you know that? Because this is sine of theta plus theta, and you do sine cos cos sine for the sum of the angle, sine cos cos sine, and this is what you get. So this is the equation for r. And why is important to use the double angle equation? Because now you clearly see that the maximum range happens at 45 degrees, because if theta is 45 degrees, to theta is 90, and that's when sine is maximum. You know that sine is maximum at 90 degrees, and our max is b naught squared over g at theta equals 45 degrees. Or you could take the derivative. The derivative of sine is cosine. Cosine is 0 cosine is 0 at 90. So 2 theta equals 90. So if you take the derivative of this respect to theta, you get a constant, probably negative 2 b naught squared over g cosine of 2 theta. This 2 is this 2. And cosine is 0 if 2 theta is 90. So theta is 45. So this is the first one. I mean the second equation. We got this one. And now we are going to find the height The height, we could just use the y equation. Let's separate this by topics. So you put the y equals b naught sine of t minus 1/2 gt squared. And you know this happens at half the time of flight. But if you want to prove it, just take the derivative of this, that is this, and equals to 0, and you get this time. You get this time. So you find the derivative of y, that is the velocity. And when the velocity is 0, what is that time? And you know that that time, let's call it times half, is tau over 2, which is b naught over g sine of t angle. We are going to substitute this over here. Now, put over here, so you get y b naught square over g sine times sine is sine square minus 1/2. 1g cancels, so you end up having b naught square over g sine square of 1/2. 1 minus a half is a half. We call this h is and this is the equation for h. All right, let me recap it over here. So this is 0, 0. This is r0. It's the quadratic function, and this is r over 2, 0. So let's verify that this is indeed, h. Let's verify that that is indeed half the range. How we know that? We know the equation for x, and we put the tau divided by 2, time of flight divided by 2, which is b naught g sine of the angle, and you get b naught square over g sine cosine, and we multiply by 2 and divide by 2, and we get 1/2 b naught square over g sine of twice the angle, and this is r. So x is r over 2. So this is in the r over 2. This is the height, and you could think it this way. We have g, the initial velocity, and the angle, and you could have the problem written in terms of r, h, and tau. So the range, the height, max given the angle. Max is when the angle is 45, and this is the time of flight. And the equations are and these are the equations for the range, for the range, for the height, and the time of flight equations.